potable water is water that is suitable for drinking. So drinking water is technically called potable water. Now, when we're looking at the availability of water on the planet for humans, obviously we're interested in potable water, water that can be used for drinking, and water that can be used for agricultural resources, for watering crop plants. So we're looking not just at the quantity of water, but also at the quality of water. Earth has lots and lots of water on it, but a very small amount of it is of the quality that we need to be able to use as potable water. And the WHO estimates that about 25% of the world population does not have access to safe drinking water. Now, if you remember that our population is around about the 7 billion people mark, that means that about 2.75 billion people don't have access to potable water, safe, constant access to fresh drinking water. Huge numbers of people. It's obviously of large importance to environmental scientists. Now, Earth from space looks like a blue planet because most of the Earth is covered with ocean. There's much more ocean surface than there is land surface. However, salt water can't be used for irrigating crops. It also can't be used to drink. So if we look at how much fresh water there is on the planet, only about 3% of all the water on the planet is fresh water. Now, of that fresh water, large amounts of it are locked away as ice and snow in the polar ice caps or on our mountain ranges. Some others deep down within the ground where it's unreachable for most populations. So of that 3% that is fresh water, only a small fraction of that is actually available to us. So when we look at all the water supply, we have only about 0.003% that is available fresh water for human use. So if we had 100 litres, then of those 100 litres of water, the equivalent percentage would just be 1 teaspoon. So tiny fractions of the water that's on the planet is actually readily available for human use. The good news is that that small portion of available fresh water is continuously cycled through the planet and cleaned by natural processes. This cleaning cycle that keeps on moving that available fresh water through the planet is called the hydrologic cycle. Now, the hydrologic cycle in high school was probably called the water cycle, and most people should be aware of this, where we see evaporation of water into the sky, condensation into clouds, the clouds causing rain or precipitation, and then that precipitation running down rivers back to the ocean. So I'm assuming that the hydrologic cycle is not completely brand new to you. We do have to give it a few more biological terms though, and the first one is this idea of evaporation. So we do get evaporation of water from lakes and rivers and oceans, and that evaporation of the water is what eventually will go into the sky to produce clouds. But at our level we need to understand that it's not just evaporation from lakes and oceans that matters, it's also evaporation of water from plants. Now, the evaporation of water from plants is given a special name. It's called evapotranspiration. The transpiration is the loss of water from plants. So evapotranspiration is water that's sucked out of the ground by our local trees, our local grasslands, and that water is then passed into the air, passes up into the sky, and can then form clouds. Those clouds will do precipitation, that is snow, ice, hail, rain, fog, and the water that's in those clouds will be brought back down to the ground. When it hits the ground, it now has two fates that can happen. The first fate is that the water can run off, and as it runs off the ground, it's called runoff. So streams and creeks and rivers are examples of runoff. Looking at the water running in the gutter on the side of the road, that's an example of runoff. The second fate is that it can enter into the ground. It can seep into the soil. And that process where it seeps into the soil is called infiltration. It will infiltrate the ground. And once the water has infiltrated the ground, it then becomes groundwater. It's no longer runoff, it's not running off along the surface of the ground, it's now inside the ground, so we have groundwater. That groundwater will soak down through the soil, moving down and sideways until it reaches a permeable layer where water can actually build up within the soil and rock. These permeable layers that accumulate water are called aquifers. So aquifers are areas of stored groundwater. Now, it is very rare for an aquifer to be an actual pool of water under the ground. No matter what the show on move is, it's rare for it to be a big pool underground river. More often, it is a permeable type of rock. So it's going to be coarse sand, gravel, or a very permeable cheese, Swiss cheese-like, sponge-like rock. So the water will fill up this permeable area and produce our underground aquifer. Now, if we tap into that aquifer, we have the ability to then use groundwater for our water source. Now, if we're removing water from an aquifer, it needs to be recharged, needs to be refilled, so that we don't run out of water. So somewhere the aquifer has to have its recharge zone. So we say that an aquifer is recharged. Rain will land on the ground, soak in, infiltrate again, and refill the aquifer. It's recharged. Not all aquifers have recharge zones. Some aquifers are said to be fossil aquifers, and fossil aquifers do not have a recharge zone. Most of our fossil aquifers were produced at the end of the last ice age, and as the glaciers melted and the snow melted, that water infiltrated the ground and filled up our aquifers. Now, normal rain does not recharge those aquifers to any significant extent, so if you remove water from a fossil aquifer, it will not be refilled. All that will happen is the amount of water in the aquifer will go down and down and down until you completely run it dry. So we should have a good idea of what's happening in the hydrologic cycle. What I want to focus on is, so how are we changing the processes that are occurring in the hydrologic cycle? As the human population has increased in size, as we become more urbanized, what is happening to the hydrologic cycle? The first impact humans are having on the hydrologic cycle is that we are increasing the amount of runoff and decreasing the amount of infiltration. So as precipitation happens and it lands on the ground, more of that precipitation is running off into rivers and creeks and streams, and less of it is soaking into the soil and becoming part of the groundwater. And there's four main reasons that this is happening. The first one is urbanization. When we build urban areas, we build homes, we produce roads, we make pavements and driveways. All of those items put hard surface right on the surface of the ground. Concrete, tarmac, roof tiles, asphalt. And as we put these hard surfaces on, they prevent the infiltration of water. And that water is fed off of our roofs, down gutters, down spouts. When it reaches the ground, it's fed down gutters into drainage ditches and drains, and those drains carry that water away to our local creeks and rivers. So this rainfall is fed deliberately away from our living areas to prevent flooding. Now, without sitting on the ground and giving it time to soak in, it means that infiltration that would have naturally happened is reduced and runoff is increased. The second impact we're having on decreasing infiltration and increasing runoff is deforestation. So by cutting down trees, we're decreasing the amount of water that soaks into the ground and increasing the amount that flows off. On our slide here, we have the results of an experiment where they took a watershed being an area of land that feeds water into one particular river system, and they clear cut it. So they chop down all of the trees in that area. And you can see that in 1935 there was very, very little water in the streams. The streams were fairly consistent in their depth, but had fairly small amounts of water in them. Then when they cut down all the trees and they come back and they check the actual size of the streams have large amounts of water in them, the streams are flowing extremely quickly, and the streams show large amounts of variation, periods with very low water flow, periods with very high water flow. Now as the trees grow back, as the vegetation regrows, the depth of the water in the stream decreases. But as the depth of the water in the stream decreases, rather than showing as much variability being really deep water one week, very shallow water the next week, that variability also decreases. So the average amount of depth of the stream is lower, but it's that depth for many more days. So what we were seeing at the beginning with a clear cut is a stream that one day would be in a raging torrent filled with water and just pouring down the mountainside. Then a week later it'd have virtually no water in it. And then when it rained, it'd be a raging torrent again. And then a week later it'd have virtually no water in it. As the vegetation grows back, the average depth of that river goes down, but it stays about an even amount. So it never is a raging torrent, it never is virtually dry. Instead it's just a middle river day after day after day. And the reason that's happening is because the tree roots and the tree leaves that have fallen on the ground and produced a mulch-like layer is acting as a sponge. They're acting as a hold on that water. They're trapping water and allowing it to soak into the soil. Then instead of being runoff, that soil is moving the water as groundwater towards the stream. So it's taken a really long time for this water to move through the soil to make it to the stream. So it may reach the stream not the day that it rains, but it may reach the stream 2 weeks after the rain event happened. So the stream is always being fed small amounts of water. Now that means that the stream is a nice stable habitat, and because it's a stable habitat, it can support large species numbers. On the other hand, if you cut the trees again, and you see that in 1965, then all of a sudden there's nothing to trap that water. Rather than sitting in the grooves generated by the roots, or sitting amongst all that piled up leaf decay, the water just flows off the soil, flows into the river, and the river goes into spate, goes into flood very quickly. And once the water's washed away, there is no more water to fill it. So then the water will drop down to virtually no amounts when it's not raining. So we're back to this big flood, then no rain, then big flood, then no rain cycle. So as human population increases and we start cutting down more trees, we're decreasing the amount of water that has time to soak into the soil. And because we don't let it soak into the soil, rather than being slowly released into the environment, it leads to rapid stream spate. Rapid stream spate is another word for saying rapid stream flooding. So the stream fills up very rapidly. So we're decreasing the amount of infiltration and we're increasing the amount of runoff. And that runoff increases the likelihood of severe flooding. The third and fourth impacts that we're having to cause increased runoff and decreased infiltration are overgrazing and overcultivation. And these two go hand in hand. Overgrazing is putting too many animals on a field so that they decrease the amount of vegetation on that field down to virtually nothing. They just eat up all of the grass and we're left with just a soil sandy looking field. Overcultivation is where we plough the field too often, and rather than having a constant cover of crop over the ground, we plough the soil down to just bare soil and have it exposed. Now both of these have a double whammy effect, and the first one is that rather than having plants to act as a sponge to hold in the water, to hold the water in place and give that water time to soak into the soil, Without any of those plants, the water can just flow off of the ground. So what's happening is the plant barrier is not there to hold water, to keep the water in place, to give it time to soak into the ground, so it just runs off the soil. The second part of it is that there's no plant barrier, and that plant barrier is not shading the soil from sunlight. And because of that, the sunlight beats down on the dark coloured soil and dries out the upper layers of the soil. That dry upper layer becomes impervious to more water penetration. So as the water leaves the soil, it actually means the soil has a much harder time of then accepting more water. So without the plant barrier, water doesn't sit on the soil as long to infiltrate, and the soil is less likely to soak up water. So both of those things mean that when it does eventually rain, that rain is much more likely to wash off the soil and become runoff. So notice that we now have a continuing cycle. The soil gets drier, which means it's less likely to soak up water when it does rain, so the soil becomes drier, which means it's less likely for the soil to soak up water when it does rain, so the soil becomes drier, which means it's less likely that the soil will soak up water when it does rain. So we get into this continuing cycle of the ground becoming drier and getting more and more runoff. The second thing that human population is doing to the hydrologic cycle is increasing the sediment load in our runoff. So our first one was saying, hey, we've got more runoff now, less infiltration. Well, as that runoff is going over our fields and over our work sites, it carries with it dust particles and sediment that are there. We just talked about this idea of having a farmer's field with no plants on it. Well, when it does rain, that rain runs off of the field and takes with it that top dry layer of soil. So it's washing away the topsoil. If we have a building site in a city, then when it does rain, the exposed soil gets picked up by the water and flows off into our storm sewer system. So when we look at our local rivers, when we look at our local creeks, they tend to be very turbid. Turbidity is a measure of how much particles there are in the water, how much sediment is floating in the water. So these two pictures show creeks and ponds during rain spate, during a heavy rainstorm, and you can see how turbid they are. They have large amounts of sediment. Sediment in large amounts has a very negative impact on our waterways. Normally what we'd like to see in a waterway is a good penetration of sunlight. That sunlight allows algae and plants to do photosynthesis, and therefore we have primary production within our river. Primary producers allow consumers to feed on them, and consumers allow other consumers to feed on them. So we build up a food chain within the river. If you have large amounts of sediment in your river, then you don't get that food chain production. The sediment prevents sunlight from penetrating, the plants can't grow, so we have no primary producers. If there's no primary producers, then we're not going to see the levels of herbivores feeding on them, and without the herbivores we don't get the carnivores. So if we get large amounts of sediment placed into our rivers, it can completely disrupt the food chains that naturally would be present. Not only does it prevent photosynthesis, but that sediment load will also smother the eggs of fish and aquatic insects that are living in the river. Many of our fish lay their eggs on the bottom of the river, and with a high sediment load, that sediment gets dropped out, gets dropped onto the bottom, smothering the eggs, suffocating them and killing the eggs of the fish that were living there. So if we compare a natural stream with not as much runoff, more constant runoff, and lower levels of sediment, it will very often have much higher levels of biodiversity than streams with extremes of flow, high levels of flow followed by low levels of flow, and large sediment loads. And the third and last thing that human population growth is doing to our hydrologic cycle is that we are decreasing transpiration. So here we got a picture from a tropical rainforest, and you're seeing steam coming off of the trees in the morning. The trees are transpiring. They're doing transpiration, evapotranspiration of water into the air. So they're doing their evapotranspiration of water into the air. That water will pass up, generate clouds, and cause rain. If you go into this area and cut down all of those trees, then they can no longer do their transpiration. They can no longer take soil water, move that soil water into the air, and generate the conditions needed to produce clouds. So by cutting down trees, you can actually change the cloud formation in that area. So by cutting down large amounts of trees, you can change rainfall patterns in that area. Now, as the world population grows and we start to deforest areas, that means we're having an impact on the temperature of that area, not only by changing its albedo, but also by changing cloud formation and rain amounts. The class's discussion forum is going to focus on how we can overcome some of those changes to the hydrologic cycle. So for this lecture, I want to look at two other problems that humanity faces with water on our planet. The first problem we're going to deal with in this lecture is going to be the lack of fresh water, and then in our next lecture we're going to look at water pollution issues. So for this lecture, we're going to focus on lack of fresh water. Now, we know that parts of the planet are definitely facing freshwater shortages. And fresh water is one of the limiting factors for most populations. So let's start by looking at the causes of freshwater shortages. And after we've done those, then we'll go on and look at ways to actually increase the amount of fresh water available. So our first cause of freshwater shortage is just a dry climate. And right here we have a photo for the airport at Las Vegas. And why does Las Vegas have a shortage of fresh water? It's because the city is built in an area that has a dry climate. The climate of the area is the average weather, and Las Vegas is in an area where it rarely rains. So if you put large numbers of people into an area with very little rainfall, you should expect to have freshwater shortages. There is no way to fix dry climate. We do not have the ability to all of a sudden change the way the wind blows, change the way clouds form, so that it will now rain on a place where we want to build a city. So with dry climate, there's really only one fix to that, and that's don't have a large population living where there's a dry climate. If you live in an area of wet climate, then freshwater shortages are not going to be an issue. If you live in an area with dry climate, freshwater shortages are always going to be an issue, particularly if you allow your population to grow. And in Nevada, they're allowing their population to grow, and they're pushing right up against their ceiling for their ability to provide enough fresh water to everyone. And there really is only one way to control this, and that's don't live where it doesn't rain. The second cause of freshwater shortage is drought. And drought is a period of abnormally low rainfall. So even if you were to live in an area that had adequate rainfall, you're going to have years where you get below normal rainfall, and they would be your drought years. And during drought years, it would be expected that there would be a shortage of fresh water. So here we've got our picture again from the Ethiopian village, and there are times when there is plenty of rain and the crops grow, and there's times when there's much less rain and the crops fail to grow. What's interesting about this picture is that some of this drought is actually caused by the human activity. If you think back to our previous section on human influences on the hydrologic cycle, we said that overcultivation and overgrazing will change the amount of water that soaks into the soil. And this was a classic example of that. You can see how the ground has absolutely no plant life growing on it. Once the drought started, the plants could not keep up with the number of animals, so the animals were overgrazing the ground. Once that overgrazing occurred, it meant that the land was less able to absorb any rainfall that did occur. The rainfall was very low because we were in a drought period, so when we did get a small amount of rain, it didn't soak into the soil. Because it's not in the soil, the plants don't get it, so more plants die, and then you're in a nasty cycle of drought leading to the loss of water from the soil, and therefore that leading to plant death, which leads to herbivore death. Now, again, we cannot cause rain to happen, so drought is something that we're going to have to live with. And the third cause of freshwater shortage is water stress. And water stress is the fact that just too much water is actually being used. Now, water stress obviously overlaps the other two. If you have a population living in a dry climate, if your population is small, then you can probably utilize the water even though you have a dry climate. As your population increases in size, that's going to produce water stress. You're using more water than is being delivered to that area. And drought would make that even worse. If you're in a dry period and you've got a large population that's using lots of water, then you become water stressed. So water stress makes the other two areas much, much worse. And water stress is what we're seeing in large amounts of the US. Right here in Georgia at the moment, we are in a drought, and we're also seeing large amounts of water stress near our cities, where large cities are using large amounts of water and making the effects of the drought worse. The drought's not worse there, it's just that because they use so much water in our cities, the effect of the drought is worse. So that was reasons why we're facing water shortages. And now we're going to deal with, okay, well, if we have a shortage of water, how are we going to obtain more water? How are we going to get enough water to keep our population healthy? And there are 5 basic ways of doing it. We can build dams, we can do water diversion projects, we can utilize groundwater. These ways are all ways of trapping or finding new water sources. And then the last 2, conservation and technological solutions, are ways of utilizing the water that we already have much more efficiently. So let's start with dams. You can easily increase the amount of water that you have on hand by building a dam. And dams will always be necessary because we have this idea that droughts lead to water shortages. And there's no way that we can prevent droughts. So if we're going to have periods where we have abnormally low rainfall, there has to be a way to store that water so that in a year of low rainfall we have water to use. So dams are a vital source of utilizing storage of water to survive during drought times. Now, dams have huge numbers of benefits, as well as just providing water for drinking in our cities. Not only do they provide a nice stable supply of drinking water, they also provide a huge recreational facility. So they can be useful for developing an economy of an area. And not only can it be used for recreational fishing, in some countries it's also used for commercial fishing operations. Well, they'll dam a river, produce a large lake, and then commercially fish that to supplement their food supply. Now, dams may also be used to produce hydroelectric power. It is true that most large areas in the United States that could be dammed have already been dammed. So the expansion ability for large-scale hydroelectric within the United States is not that great. But small-scale dams with smaller-scale hydroelectric power stations could be built. The dam also reduces downstream flooding, as long as the dam doesn't break. If the dam is holding back water and releasing water at a slower rate than normal, they can have a mitigation effect, a reducing effect on this peak and trough idea that our increase in runoff has caused. Remember that humans have increased the runoff caused when it actually rains. And that leads to rivers filling up very rapidly, and that leads to flooding. If you place in dams, we can reduce that somewhat. It may have been more efficient to have just allowed that increased infiltration and allowed the natural environment to reduce the flooding downstream. But if we want to trap water for drinking anyway, then the dam can have another positive effect of reducing downstream flooding. Dams are not all cheery good things though. They also have some downsides. The upstream area from the dam is going to be flooded, and that will flood natural habitats and displace some people. So we see that areas that are building dams often had protests from people that are having to move out. Dams also entrap large amounts of water that are exposed to sunlight, and therefore they lead to evaporation. So by trapping that water there and having it exposed to the sunlight, whereas if it was soaked into the ground, if infiltration would have happened, the ground would shield it from the sunlight and we wouldn't have that evaporation. Comparing groundwater or lakes produced by damming, the lakes produced by damming lose much more water through evaporation. So they're not the best source of storing water. A good source, but not the best. The dam also prevents downstream flooding. And believe it or not, downstream flooding is a good thing for farmers. Floods take new nutrients and new topsoil onto the floodplain. So farms on floodplains, they're often called alluvial farms because they're on the alluvium, the flood soil, are extremely fertile. And these nutrient-rich soils make excellent croplands. If you prevent this flooding from happening, then you don't refresh those croplands with new nutrients, and the farmlands are not as productive anymore. So flooding may be seen as a bad thing in the short term, but in the long term, flooding can lead to extremely good quality farmland. And the last big downside of the dam, that would be the disruption and migration of spawning fish. California used to have very large salmon stocks, large salmon populations that they commercially harvested. California put in large dams on virtually all of their rivers, and those dams prevented the salmon from moving upstream so that they could no longer breed. And when they no longer bred, their population crashed, and now California has no industrial scale salmon farming because their population have been destroyed. So putting in a dam will definitely disrupt the migration and spawning of some fish species. It will improve habitat for some fish species. Largemouth bass live behind the dam excellently all over the United States, but for migratory species like salmon and some trout, it decreases their population. So dams can be used to increase the amount of water found in an area so that we can survive during drought times. But what happens if that area physically doesn't get enough rain? Well, if there's not enough rain because you're living in a dry climate, then one way to do that would be to deliver rain from another part of the country. So this would be called a water diversion project. You're diverting water from one area into a different area. So we're moving water from one watershed, the watershed being that land area that supports one river, and collecting that water and moving it to a completely different watershed. Now, one of the largest water diversion projects that we have is this series of aquifers and pipes in California. One of the main downsides of these water diversion projects is that they take water from one system and place it in a separate system. So everything in the first system downstream of the water diversion project receives less water than normal. So we're sucking water out of one river, and everything downstream from that point is going to have much less water in it. So we're impacting the environment of one river to support human life in a different area. A great example of this is the Aral Sea over in the former Soviet Union. what was happening is that the Soviet Union really wanted to generate a very large market garden farming area. Market garden is producing crops like lettuces, cabbages, radishes, potatoes, all of the vegetables that we would normally eat. And this area of Kazakhstan and Uzbekistan, between the two rivers here, the Saya and the Amur, really does not receive enough rainfall to support the industrial farming that they wanted to produce there. So they decided to irrigate them, and they used water diversion from the two rivers to actually irrigate this area of land in between them. Now this made it a major farming industry, and huge industrial farms producing most of the market garden crops for the former Soviet Union. All the water being sucked out from those rivers, though, meant that the area downstream was receiving much less water flow. And as that water flow decreased, the size of the sea, which is actually a freshwater lake, it's an internal lake, dropped. And you can see that the lake shrank and shrank and shrank. And in fact it then became two separate pieces. The Uzbekistan section was separated from the Kazakhstani section. Now as the water level shrank, the fishing industry in the Aral Sea was completely decimated. And therefore the area that used to have the ability for two industries to function, both fishing and farming, ended up with only a farming industry. So by supporting one industry in one area, they destroyed the habitat in another area. That had negatives not only for the human population or the people that were fishing, but also had negatives for the wildlife within the Aral Sea. As the amount of water disappeared, the salinity or saltiness of this zone increased and really did kill off large amounts of areas. So large numbers of fish populations and wading bird populations were just devastated by the loss of this area. How'd you get the Aral Sea back? Well, you get it back by not sucking the water out the rivers and allowing those rivers to fill up the Aral Sea again. So by decreasing the water diversion project, the Aral Sea could become healthier once more. And that's what we've seen since the breakup of the Soviet Union, as this actual market garden area has decreased in its water usage. The Aral Sea has started coming back and now supports some small fishing operations again. So we've got this issue with water diversion projects. Water diversion projects move water into one area and does help support the human population in that area, but only at the cost of reducing the water to its original area and pushing down the ability of that original area to support wildlife and its human population. So there's no net gain here. What it is one area is gaining while one area is losing. The third way that we're going to provide more water for an area is we're going to do groundwater mining. We're going to dig down into our aquifers and utilize our groundwater. Now, using groundwater has many advantages as well as disadvantages, just like our other ways of producing water for an area. Now, groundwater is water that's sealed inside aquifers, so it's surrounded on all sides by land. So it's not exposed to sunlight. And because it's not exposed to sunlight, there's no evaporation from our groundwater. So with no evaporation, groundwater makes an extremely good long-term storage site. So we can seal the water in there and know that it's not going to be decreased in amount every time the sun comes out. Not only that, it's available year-round. This is not a seasonal flowing river that works every time we get snow melt in the spring. It's there year-round, year after year. So it's a good long-term source of water. Not only is it a good long-term source of water, they're also plentiful, with large numbers of aquifers spread around the country, so they're easy to find. And not only are they easy to find, all you have to do is drill a well to be able to extract that water. So unlike a dam with huge construction costs, or a water diversion project where the pipe work and canal work is going to cost large amounts of construction money, all you have to do is drill a well. So of the previous choices, utilizing groundwater is by far the least expensive. And not only that, due to the filtering through the soil, you tend to get very high quality water from our aquifers. So we're getting high quality water available year round for not large amounts of money. Sounds like the perfect example. The disadvantages, though, are also fairly big. The first disadvantage is the idea of aquifer depletion. Aquifer depletion means that the aquifer starts to run out of water. If we're removing water faster than the recharge of the aquifer, faster than rain can soak into the ground and move through the soil to refill the aquifer, to recharge it, then the aquifer will get smaller and smaller. The problem here is that you don't see it happening. In a lake, you see the lake getting smaller as we suck water from it. Under the ground, we don't have that visual cue. We don't see the aquifer getting smaller, so we don't modify our behaviors before we try and suck water out and find that it's no longer there. And when we find that the aquifer has shrunk is when we try and suck water out of it and the water is no longer there. And that's a little bit too late. So aquifer depletion is a large problem. Not only do we get that, we also get sinking of land. When you remove the water from within those rocky substrates, you move some of the support, so you tend to get pockmarking of the land. Now, underground aquifers often feed underground rivers, and those rivers often flow water into surface water, lakes and streams and rivers. So if we are using up the water underground, then that's going to reduce the flow into surface waters at springs. So by utilizing an aquifer in one area, you can indeed stop river flow in a separate area where the aquifer was to flow out. A great example of this is on the Gulf Coast of Florida. There's a place on the Gulf Coast of Florida just across from Gainesville called Crystal River, and the town just lower than that is Homosassa. Both of these have large numbers of aquifers that flow out into rivers that then flow into the Gulf of Mexico. And the fish populations in these zones are changing over time. The fish populations are changing because the rivers are becoming saltier and saltier. It used to be that the aquifers had large amounts of water in them. That water would discharge from the aquifer in through springs, and the springs would feed the rivers being very, very short, that would carry this fresh water out into the Gulf. And within those freshwater springs, large numbers of freshwater fish would live. Then fish that are adapted to live in estuarine areas would live in the mouths of those rivers and creeks. As the population has grown, the flow rate of water out of the aquifer has dropped dramatically, which means that most of the creeks are now very, very salty as the salt water has moved inland. And that saltwater intrusion has then meant that marine fish have moved into those areas. So where people used to go and fish for bass, now you can fish for snook. So we're seeing changes in the environment because we're decreasing the flow of groundwater by withdrawing groundwater faster than recharge can occur. And the last problem that we're going to do on this slide would be contamination. Groundwater generally moves very, very slowly. So if we do contaminate a groundwater system, an aquifer, unlike a river that flushes out on a daily basis and would carry that pollution away, the pollution in an aquifer will sit there for many, many years. So once one is polluted, it's extremely expensive, if not impossible, to clean that pollution out of the aquifer. So we know that the population of the United States and indeed the world is increasing, and here's a quick map of aquifer overdraft. So an overdraft on your bank account is when you remove more money than you had coming into your bank account. An overdraft on an aquifer is when we're removing more water than is flowing into the aquifer. So you can see here in Georgia, we are removing more water than we actually have flowing into our groundwater. So we're showing an aquifer. Our groundwater levels are decreasing faster than they're being recharged. It's even worse out in the middle of the US, where we do large amounts of aquifer-based agricultural watering, where we're actually irrigating our crops using groundwater. And this big red patch in the center here, that's actually the Ogalla aquifer, and the Ogalla aquifer is a fossil aquifer. It has no recharge, and because it has no recharge, as we do withdraw water from it, there is no refill, so therefore we have a very high overdraft. We're sucking water out and it's not being replaced. Obviously that's worrying, because the amount of farming that we do in this zone and how vital the food production here is for our economy. So aquifer depletion is probably the #1 problem with using groundwater as a water source. You have to control your population, and you have to make it so that the aquifer does not become empty. You have to match the water withdrawn from the amount of water flowing into the aquifer, otherwise it's a non-renewable resource. We need to be able to utilize these aquifers in renewable ways, in ways where the water is replaced at the rate that we use it. That's the only way we can do it sustainably. So if the Ogalla aquifer is our example of a fossil aquifer, and we know that we have to use our water sustainably, so that we don't utilize all of the groundwater that's down there and leave none for our offspring or for their offspring, we need to look at ways of utilizing water more efficiently, and that's what we're going to do in our next series of water lectures.